Hello everyone, in the last lecture we discussed a metric on the set of real numbers. Can you recall what that function was which we proved to be a metric? We had defined the function as d from r cross r to r as d of xy is equal to mod of x minus y. This was the function, and this function we proved turned out to be a metric. So this was a metric, and we say this metric as, we call this metric as usual metric. Now using this usual metric, we will see how many metric we can define on the set of real line. So suppose x is equal to r and a function d defined from r cross r to r as d of xy is equal to 3 times mod of x minus y. This is a function. This was our usual metric, and using that we are defining a new function. Now we'll see if this is a metric or not. Since this was a metric, that means this satisfies all those four properties. That means d of xy, or we say mod of x minus y, is always non-negative for every x and for every y. Moreover, mod of x minus y is 0 if and only if x and y both are equal. Non-negativity identification, and then symmetry. Mod of x minus y is same as mod of y minus x. Triangles inequality, that means for every x, y and z belonging to R, mod of x minus y is less than equal to mod of x minus z plus mod of z minus y. These four conditions are satisfied. So now, since this is non-negative, there is a positive number. Multiplying a non-negative number with a positive number always gives a non-negative number. This is a property of real numbers. Therefore, non-negativity is trivial. Non-negativity holds. Now, second thing is identification. If we take d of xy to be 0, this can only happen by definition if 3 times mod of x minus y is 0. What does this mean? Product of two number is 0. That means either of the two number have to be 0. This is non-zero. Then only option is that this is if and only if mod of x minus y is 0. And from usual metric, we know that mod of x minus y is 0 if and only if x is equal to y. This is if and only if x and y both are equal. Third number is symmetry. D of, we know from usual metric that mod of x minus y is same as mod of y minus x. This is for every x and y belonging to R. Non-negativity is also for every x and y belonging to R. Okay. So if this, from usual metric, we know that mod of x minus y is same as mod of y minus x. This implies that if we multiply both sides with 3, we can multiply both sides with 3. That will not change anything. So multiplying both sides by 3, we get 3 times mod of x minus y is equal to 3 times mod of y minus x. This by definition is d of xy. This by definition is d of yx. Therefore, d of xy turns out to be equal to d of yx. Now, number 4 is triangles inequality. Triangles inequality. Using usual metric, we know that for every x, y and z, belonging to R, mod of x minus y is less than equal to mod of x minus z plus mod of z minus y. This is an inequality. Now if we multiply both sides by a positive number, will that change this inequality? No, that will not. Multiplying both sides with positive number does not change the inequality. This is a property of real number. So we can multiply both sides by 3. 3 times mod of x minus y is less than equal to 3 times mod of x minus z plus 3 times mod of z minus y. This by definition is d of xy. This by definition is d of xz. And this by definition is d of zy. Therefore, all four properties are satisfied, and hence R with this D, this function is a metric space. So we have done two metric spaces. First one, we have defined two metric on R. First one was mod of x minus y, and second one was 3 times mod of x minus y. Now, what other metrics can I define? Can in general I say D from R cross R to R defined as D of xy is equal to k times the usual metric mod of x minus y. Will this function turn out to be a metric if I take k to be any real number? No, it will not. Suppose if k is negative, then d of xy, which is product of a negative number k and a non-negative number x minus y. This is a non-negative number, this is a negative number. So the product of these two will always be non-positive, will always be less than or equal to 0. So d of xy does not satisfy non-negativity. Therefore, that cannot be a metric if k is negative. So suppose if I take d of xy as k times mod of x minus y, where k is non-negative. Suppose if I delete the case of negative, k to be negative. So if I consider k to be non-negative, will this function turn out to be a metric? Non-negativity is satisfied. Since k is non-negative, this is non-negative, therefore the product will also be non-negative. Therefore d of xy is non-negative. That is trivial. Now second condition is identification. Will identification satisfy? So second property is identification. Will this function satisfy the property of identification? What does identification say? That d of xy is 0 if and only if x and y both are equal. If in case, since I have taken k to be non-negative, so there are two possibilities. Either k can be strictly positive or it can be equal to 0. If k is 0, then for any two real number d of xy, k times mod of x minus y will turn out to be 0. This will be for every x and y belonging to R. Does not matter if x and y both are equal or if x is not equal to y. For x not equal to y also, d of xy will turn out to be 0. So in this case, identification property will not hold true. That is, here we are getting d of xy is 0, but d x and not y both are not equal. If I consider this case, x and y both are different, but d of xy is 0. Whereas what we have done in identification property, that d of xy is 0, implies that x and y both are equal. Here this property is failing, hence in this case also, that is for k is equal to 0 as well, this function does not turns out to be a metric. So the only case we remain with is d of xy is equal to k times mod of x minus y, where k is a strictly positive real number. If we take k to be strictly positive, will this function be a metric? Non-negativity. Since this is positive, this is non-negative, so the product will also be non-negative. So non-negativity is satisfied. In identification case, the only problem was when k is 0. So if I take k to be strictly positive, this will not be 0. So only thing we are left with is that this has to be 0. And if this is 0, that means x has to be equal to y. So identification case hold. If d of xy is 0, this is possible if and only if k times mod of x minus y is 0. K cannot be 0 since we have taken k to be strictly positive. That means we are only left with mod of x minus y is 0. And this is possible if and only if x and y both are equal. Now the third condition, that is symmetry. D of xy is k times mod of x minus y. This is usual metric which is symmetric. We can write it as k times y minus x, and this is d of yx. So symmetry holds for every x and y belonging to R. Now fourth condition is triangles inequality. For every x, y and z belonging to R, mod of x minus y is less than equal to mod of x minus z plus mod of z minus y. This is something you have already done in usual metric case. So if I multiply both sides with a strictly positive number k, then the inequality will remain as it is, and I will get k times mod of x minus y is less than equal to k times mod of x minus z plus k times. So multiplying with k on both sides, I get k times mod of x minus y is less than equal to k times mod of x minus z plus k times mod of z minus y. This is by definition d of xy, this is by definition d of xz, and this is by definition d of zy. So hence triangles inequality holds true. Therefore all four properties are satisfied, and this D is a metric and R with D is a metric space. So now you have done that for every positive number k, with the help of usual metric, I can define a new metric space for every positive real number, and there are infinitely many real numbers, infinitely many positive real numbers. So how many metric can I define on R with the help of usual metric? Infinite metric I can define on R with the help of usual metric. So we will do a new type of metric on a new set in the next lecture. Thank you so much for watching.